State and prove the conjugate root theorem. The statement of the theorem: suppose that f is a polynomial with real coefficients, and the real part is important. And suppose that f of alpha is equal to 0 for some complex number alpha, then f of alpha conjugate is also equal to 0. Want to note parenthetically that this is true if alpha is a real number, because if alpha is real, then alpha conjugate would be itself alpha. So alpha conjugate would be just simply the same as alpha, and so the theorem would be true trivially. However, if alpha is non-trivial complex with a non-trivial imaginary part, then this is a 2-for-1 theorem. If you have one complex root, then you have another complex root for free. Okay, let's prove this. So let f of x be equal to some polynomial a sub n x to the n plus a sub 1 x plus a sub 0. And all of the a sub i's are real numbers. Then if I plug in alpha, f of alpha is equal to a sub n times alpha to the n plus dot 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 plus a sub 1 times alpha plus a sub 0. That is equal to 0 by assumption, because alpha is supposed to be a root of the polynomial. So that means if I take the conjugate of both sides, the two conjugates are also equal. So a sub n alpha to the n plus dot 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 plus alpha 1, or say a sub 1 times alpha plus a 0. If I take the conjugate of the left-hand side, that's equal to the conjugate of the right-hand side, which is 0 plus 0i. Now, what's the conjugate of 0 plus 0i? The conjugate of 0 plus 0i is 0 minus 0i, and 0 minus 0i is simply 0. In other words, the conjugate of a real number, like 0, is simply the number itself. Now, that's important as we go on throughout the proof. So let me write out 0 minus 0i at this step, and that will be equal to 0. And the important thing is that the conjugate of a real number is the number itself. Now that'll be important, especially as we proceed on the left-hand side. Okay, on the left-hand side, we have a theorem that says, from the previous review, that if I have the sum of a bunch of complex numbers, the conjugate of the sum is the sum of the conjugates. So I can write this as a sub n times alpha to the n conjugate plus a sub 1 times alpha conjugate plus a sub 0 conjugate. I also have another theorem that says that if I have the product of two complex numbers like this, then the conjugate of the product is the same thing as the product of the conjugates. So the first, or the last term here, a sub 0, will leave untouched, a sub 0 conjugate. Then we have a sub 1 conjugate times alpha conjugate. And then we have a sub n conjugate times alpha conjugate to the nth power, just using that multiplication rule n times. Now, technically, that needs to be proven by induction, but that's fairly straightforward to do. Okay, now lastly, on the left-hand side, we apply the same observation to the a's that we applied to 0. The conjugate of a real number is 0, is itself, and so I can drop the conjugates on the a's. So I have a sub n times alpha conjugate to the nth power plus a sub 1 times alpha conjugate plus a sub 0. And I can drop the conjugates precisely because the a's are assumed to be real. Okay, now if I take a look at the left-hand side the left-hand side is exactly what I started with, except instead of x's, I now have alpha conjugates. And so we have that f of alpha conjugate is equal to 0. And that is the end of the proof. So the essence of the proof is that we plug in alpha, we take the conjugate of both sides, then we use the arithmetic of complex numbers in conjugation, and also use the fact that the conjugate of a real number is itself.